So this was a tabletop accelerator. What you do is, so here's an alternating current, alternating voltage. So let's say uh, you're accelerating a proton. When the so what you do is you make the proton, here's a strong magnetic field which will make a proton go in a circle. So when the proton gets here, what you do is you make this negative and the proton will accelerate. Then the magnetic field will make it go in a circle. When it reaches here, you make this negative. It speeds up. So it's speeding up across the gap. The magnetic field is making it go in a circle. And again, when it comes to this gap, you make that negative. Okay? So the faster it's going, the bigger the circle it's going for the same magnetic field. And when it reaches its maximum speed, you spit it up. So here, this is a cyclotron. So this was the first cyclotron, which was about this big. And now what is the biggest cyclotron? The Large Hadron Collider. This has become, the diameter has become 60 kilometers from here to second, 27 kilometers. Five kilometers. So from here to Ormond Beach, that's the diameter, a little past Ormond Beach. That's how big this guy is, the small circle. That's the current one. That's the future design. So a cyclotron to accelerate the proton to 1/10 the speed. Okay, so this is, you want the proton to come out at 1/10 the speed. The field will have a strength of 1.5 Tesla. This field will have a strength of 1.5 Tesla. Okay, so the stronger this field, for this same cyclotron, you can make the proton come out faster. Okay. Determine the rotational period of the circulating protons and the maximum radius of the proton's orbit. Okay. So here's the formula for here's the radius formula that we'll use, and here's the cyclotron frequency. Where the heck is the cyclotron frequency? Here's the cyclotron frequency. Okay, that's the angular frequency. 2 pi f is the number of times it'll make a circle. Okay, and so the cyclotron frequency is QB over M. And so that's the frequency at which you're switching the polarity of that thing. That's the frequency of this alternating source. Okay? So it becomes negative at the right time and so on, or twice that frequency. Rotational period. So this is 2 pi f is that QB over M, and the frequency is related to the period like that, QB. So that's the time it takes the proton to make one circle. The mass of the proton is 1.67 times 10 to the minus 27 kgs, roughly that. The charge of the proton is 1.6 times 10 to the minus 19 coulombs. And this is a 1.5 Tesla field. So the period is, that's minus 8. So 44 nanoseconds. Okay, what we've calculated is the proton is making a circle in 44 nanoseconds. Okay, in the cyclotron. The maximum radius of the proton's orbit, the radius is given by mv divided by qb. So if you want to come out at this speed, that's will be the radius of the path. 1/10 the speed of light. Okay. Kgs. 3 times 10 to the 7 meters per second. So that is going to give you the size of this cyclotron. That's 10 to the minus 20, 10 to the minus 1. So 1.67 into 0.3 divided by 1.6 into 1.5 meters. 0.21 meters. That's the radius of the orbit, so 40 centimeters. The cyclotron is about this big. A cyclotron this big with a magnetic field of 1.5 Tesla, you can speed up the proton to 1/10 the speed of light. A mass spectrometer. What is a mass spectrometer?
Shoots an atom straight through and then it measures the radius.
Right. So a mass spectrometer is something that measures the masses of atoms, single atoms. Is being used to separate oxygen 16 from rarer oxygen 18, taken from a sample of old glacial ice. So you guys know this. So here's Greenland. and they'll take ice cores out of this. They'll take Greenland and Antarctica and stuff like that. So these ice cores can be 3 kilometers. Okay. And in these ice cores, there are air pockets. And from these air pockets, they get oxygen, well, it's 16, so there's O2 gas, and this has O16 and O18. And from this ratio corresponds to the temperature, is related to the temperature. Okay, so you get this ice core, this thing was laid, if it's a 3,000 kilometer, this ice fell 1,000,000 years ago. This fell 900,000 years ago, 800,000 years ago. Okay, so you measure that, you know the temperature 400,000 years ago. Okay, so that's how they do that. And for that, you need the mass spectrometer. Okay, so mass spectrometer is being used. Okay, so and what's going on? Oxygen 16 is lighter, will go on a bigger radius. Oxygen 18, which is heavier, will go on a smaller radius. From the brightness of these spots, it hits, and from the brightness of the spots, you know the ratio of the two isotopes. Okay. All right, so the relative abundance of these oxygen isotopes is related to the climatic temperature at the time the ice was deposited. The ratio of the mass of the two ions is 16 to 18. The mass of oxygen 16 is that much, and they're singly charged and travel at 5 meters, 5 times 10 to the 6 meters per second in a 1.2 Tesla magnetic field. What is the separation between their paths? Okay. So what they're asking is, what is the separation between the paths? So 16 hit here, 18 hit here. They're asking this separation. Okay. The radius of the path is mass times velocity divided by QB. Okay. And the mass of oxygen 16 is given. We know the velocity. So they've gone through the velocity selector and we've selected this velocity. Okay? So the radius of oxygen 16 is, mass of oxygen 16 is so this is these are single atoms. They're not oxygen molecules. kg. And the velocity is 5 times 10 to the 6 meters per second. The charge is 1.6 times 10 minus 19 coulombs and 1.2 Tesla field. So this radius minus 20 minus 1, so 0.266 into 5 divided by 1.6 into 1.2 meters. Okay, so the radius of the oxygen orbit is this, about 1.4 meters. So it's going in a circle like that, oxygen 16. Okay. Now to calculate the radius of oxygen 18, radius is mass velocity QB. Mass 18 V QB. Mass 18 is mass 18 over mass 16. Mass 16 V QB. Why did we write it like this? This we just calculated. That's R16. So this ratio is 18 over 16. 18 over 16 R16. 18 over 16 times 0.69 meters. That's 0.99 centimeters away, the radius, okay? So here's oxygen 16, and oxygen 18 is over there, 20 centimeter gap. Those signals are not going to get mixed up. Okay.
Go back to the other page.
And again, so this is the story. Okay, so you're getting a 3 kilometer long ice core. Air pockets are trapped, so there's oxygen trapped, and you're measuring the ratio of these two isotopes. And from that ratio, you can get the temperature. So you have a temperature record of 1,000,000 years, 800,000 years. Yeah. So here's Antarctic ice core temperatures. You see, here's the temperature variation, and this is 500,000 years worth of temperature data. And it's correlated to CO2 concentration.